Hello.
Good evening, sir.
Yeah, good evening to all.
Good evening, sir.
Good evening.
Good evening.
Good evening. Yes, so today we will start with the C structure manual design. So far we have learned a lot of commands regarding the Staad Pro software. Uh, Gradually we will also learn the Staad Pro, but before that we will start with the basic concepts of the steel structures. So can anybody tell me what kind of forces come in the steel structures or any structure rather? Yes. कौन कौन से फोर्सेस रहते हैं स्ट्रक्चर्स में?
Axial force, tension force,
So it may be axial may be tension
compression.
or compression. What else is there? So axial force is one thing. Second is bending. If there is a beam, then we have a bending moment. So we get bending stresses. So bending stress, it may be tensile stress or it may be compressive bending stress. So mainly these are the forces actually in any steel structures. So generally steel structures, we don't allow any torsion. So I'm not taking that torsion into consideration. So tension, compression or bending stresses, that's it. So axial forces generally come in columns. I think all of you know this. We get these forces in columns or suspension cables. In columns, we get compression. In suspension cables, we get tension. And bending stresses we get in beams. And also we get the bending stresses in columns also. Don't forget that. Column also is subjected to the bending. Okay. Now let's say fundamental or basic part of any force, which is nothing but a axial force. So this is, we can say this is very, very conceptual force. Even in bending, you will see that there is a tensile force. There is a compressive force. That means ultimately the axial forces are the fundamental forces. And bending forces or bending stresses are indirectly axial forces. Because we form a couple like this. So there is a compression, there is a tension and the couple, then it becomes the bending. Okay. So ultimately what we can say, axial stresses are the final forces in any structure. And we will see the fundamental and basic and simplest force, that is nothing but a tension. So can anybody tell me what is meant by tension? Yes, what is tension? Tension is what?
Extension of component.
Yes, so if there is a member and there is a force applied to that, and if that member gets extended along the axis of the member, then I can say it is a tension. So there is a elongation due to this force. So previously the length was, let's say L, then it is becoming L plus delta L. Total length is becoming after the force application L plus delta L, means we can say it got elongated. As it is getting elongated, then I can say this force is nothing but a tension force. Okay, so this is the basic part. Now, can anybody tell me, let's say it is a square shape of the member. The plan of the member or cross section of the member is square, let's say. Okay. For example, if you see the cross section like this, then you say the square. So the square is having some dimension B and dimension D. So can anybody tell me, now let's say I'm saying this material is a steel material. So due to application of this tensile force, what will happen in the member? क्या होगा इसमें? What will happen inside the member?
Stresses will be developed.
So stresses will be developed within the cross section, within the material, whatever material is there inside this. So as this is axial force, okay, and as this is a tension force, tension and axial also. So what kind of stresses will develop in this? The stress will be tensile stress, tensile axial stress. See, each and every word is important. Tensile is also important. Axial is also important, and stress is also important. So what is tensile axial stress in this? What is stress? Axial stress? Force upon area, cross-sectional area. For example, so in this case, it will be T upon B into D. So this will be your actual tensile stress. Generally, we denote this as sigma A T. Sigma is stress, A is axial, T is tension. So this is axial tensile stress. So this stress will happen or develop in the member. Now, as we know that in structural engineering, whatever are the forces on the member or whatever are the stresses developed in the member, we don't allow the stresses to extend or exceed more than the permissible stresses. So it should be less than sigma at permissible. Okay. So where we get this? So this sigma at calculated means we calculate it through the analysis. So we get the tensile force from the analysis. We decide the sizes and then we calculate the actual stresses, that is calculated stresses. And sigma at permissible, where we get permissible stresses?
IS code.
So we get in IS code. So actually design, we know that we calculate the actual stresses and compare with the permissible stresses. And the permissible stresses should be more than the actual stresses. That is the philosophy of any design actually. Now, what is the actual tensile stress which is permissible? So let's see in detail. Now, you know that if you increase this force gradually, then you know that this elongation will go on increasing, right? So there will be increase in stress as we increase the force. Let's say in the beginning, the force was, let's say 10 kilonewton. Then we have increased this 10 kilonewton to 20 kilonewton. Then T3 is 30 kilonewton, like this. So as we go on increasing the force, the stress will increase definitely because this T is getting increased. B by D is same, area is same. So stress will go on increasing, right? And the elongation will also go on increasing. This delta L1, delta L2. Say for T1 it is delta L1, for T2 it is delta L2, for T3 it is delta L3, right? So all of you know that due to the elongation or change in length, there will be strain in the member. So strain is a term, you know that we denote it by epsilon. So what is strain? Change in length divided by original length. So that is the strain in any member. So in this case, the strain will be epsilon 1, that is nothing but delta L1 upon L. L is constant actually. Epsilon 2 will be delta L2 divided by L, right? Correct. So that means there is a strain developed in the member and there is a stress developed in the member. And as we go on increasing the forces, the stress will go on increasing, strain will also increase. So let's plot this on a graph. So let's plot this. Let's say this is a sigma, that is a stress here, and we are plotting here as a strain here. So it is a strain and this is a stress. So as we are increasing the force, stress will increase and the strain will also increase, right? So what happens if you plot the graph of the points of all epsilon 1 and epsilon 2, or we can say sigma 1, sigma 2, then it will form a straight line like this, linearly like this. Okay, till certain point. Then after that point, what will happen? There will be like this, and then even though you increase the force, it will not be linear. Strain will increase very high, like this. And after some point, it will break. So for you know that once you increase this force, after some point, this will form a neck like this, right? And after that neck formation, it will break. So there will be two pieces of this section. So what will happen at the breaking point? There will be two members like this. So it will cut actually. And then this will be like this. Correct. So it broken, or it is breaking point, we can say. So that breaking means it happens at the ultimate force. So this is your breaking point with respect to the breaking point. That means there is a certain point till that the stress was proportional to the strain. So it was a linear. For example, if the force is 10 kilonewton, then stress is, let's say, 0.001. I don't know the number. Let's say, for example, if the stress is, this is sigma 1 actually, sigma 1, and this is epsilon 1, then sigma 2, and here it is epsilon 2, right? So it is linear, we can say, and you can see from the graph here, linear proportion. After this point, actually, there is no linear proportion. So even though you are increasing the force after this point, the strain is getting increased very high. So there is no proportional limit to this. That means stress and strain relation is not linear. Generally, we know that we denote the linear relation like this. Stress is proportional to the strain till this point. So can anybody tell me what is this point? What this point we call it as?
Yield point.
So we call it as a yield point. Yield point means till that point the stress and strain relation is linear. As you increase the stress, the strain also gets increased in the same proportion. And what is the stress here? We call it as this. So yield stress. Generally, we can denote sigma y, or in technical term, we call it as a Fy. Okay, so we know that our grade of steel is defined by Fy. So can you tell me what is the grade of steel for rolled sections in steel structures? Roll means channels, ISMB, I sections, angles. So what is the Fy value for that? Yes, in general. पता है क्या किसको? 250. What is the Fy value for high yield strength bars, HYSD bars, that we use in RCC structures? What is Fy value?
415.
Yeah, so it may be 415 or it may be 500 nowadays, Newton per mm. So now in steel structures, we are more concerned with this 250 Newton per mm square. There are certain grades actually which are available nowadays, which are used in PEB structures, 310 Newton per mm square like this. Okay. But currently we are dealing with this roll section, which are standard sections, ISO sections, we can say, channels, angles, and I sections. Okay. So this Fy will be 250 Newton per mm square. And there will be corresponding strain here, whatever is the, let's say, epsilon y here. Right now, we know that do we design the members for yield stress? किसके लिए design करते हैं members?
No, sir.
And so what we do then? What stresses we take for design?
0.87 FY.
Yeah, so if it is a HYSD, then we apply the factor of safety. So for 415, we are applying 0.875, 0.87 FY. This is your factor of safety. 0.87 is the factor of safety. So similarly, for rolled sections, for grade 250, we apply the factor of safety, which is nothing but 0.6 FY. Okay. So we design for this. So this is your permissible stress. Permissible stress means what? After applying the factor of safety. So 0.6 is the factor of safety for this. So in steel structures, if you are designing the members using working stress, then it is a 0.6 FY. Okay. So are you getting this?
Yes, sir.
Yeah. Now let's go again to the tension member. Then what permissible stress I will take here? Sigma 80. 0.6 FY. So this is actually permissible stress for tension. Please keep in mind. For every force, the permissible stress is different. If it is a tensile force, so sigma AT permissible. That means it is tensile stress. Permissible tensile stress. So if you calculate the tensile stress, then you should compare with this stress, which is nothing but now 0.6 FY. If it is a bending stress, sigma AT, not AT, BT, sigma BT. So in bending, there are two stresses. One is the bending tension and second is the bending compression. So sigma BT is 0.66 FY. So the permissible stress is little different actually. So factor of safety is different for bending stress. Sigma BC permissible, it depends on, it is not, this is maximum actually, depends on slenderness ratio, which is nothing but L effective upon R minimum. And it also depends on D by T. Okay. So these are the factors. And then we get the sigma BC permissible. Then there is one more force which is pending, sigma BT. Bending stress in tension. This is directly sigma. Actually, we have written it here. Okay. So no need to write it. Now there is one more pending, which is sigma AT. AC. Permissible compressive stress. Axial compressive. It also depends on slenderness ratio, LE upon R minimum. But it has nothing to do with this D by T. Let's see, we will see this, what is D by T and that, all this. Okay. So for example, now regarding the tension member design, we are only bothered about this number. So you know the permissible stress points, sorry, not this. This one, axial tensile stress. Okay. So this is your permissible stress given in the code. Now, if you take the FY as FY, let's say 250 Newton per mm square. So sigma AT, sigma axial tensile permissible stress is 0.6 FY, which is 0.6 into 250, which is finally comes out to be 150 Newton per mm square. So this is your permissible stress to be used for design of tension members. Now it's easy to understand. Now let's say we will assume that in this case, this is a rod which is suspended to the ceiling and we are applying a force T is equal to, let's say how much? 10 kilonewton. Okay, so tension force on this rod, this force is coming, let's say 10 kilonewton. The size of this rod is B is equal to, let's say, 100 mm, and D is also, let's say, 100 mm. Now you know the force, you know the area, so you can calculate the tensile stress, actual stress. So sigma AT calculated. If you are calculating, then we call it as a cal, sigma AT cal, T upon A. So T is equal to 10 kilonewton. That means in Newton, what is that? 10 into 10 raised to 3 divided by area is 100 by 100, area of the cross section. So how much this value come out to be? कितना आएगा? 1 Newton per mm square, less than 150. Getting this? So is it a safe section or not?
Yes, sir.
But you know that actual stress is very high, say very less than the permissible stress. That means if you design this cross section for this member, is it economical? लग रहा है कि economical? Actual stress तो 1 year you're having capacity of 150, right?
Uneconomical.
So it is uneconomical. How can you make it economical? क्या करेंगे आप? Force तो change नहीं कर सकते ना? Because it is coming from the
Reduce the
analysis.
size.
So reduce the size, reduce the A. So let's say instead of 100 by 100, we are having 10 by 10, let's say 10 mm by 10 mm square rod. Then in that case, the T will be same, A will be, we will see 10 into 10 raised to 3 will be the force, and A will be 10 by 10. What is the calculation? कितना आएगा?
100 Newton per mm square.
Yeah, so it looks okay, but still you can reduce it. So instead of 10 by 10, you can still go less, 5 by 5. So, and it should be just less than 150. Then it is economical section, right? Now let's see. Once you understand the concept, you can change these sizes as you wish, as per the economical design, right? So this is the design philosophy of tension member. Now let's say in detail again. So whatever I told you. So this is given in this 4.1 clause in IS 800.6 FY sigma 80. Okay. So you have understood what is meant by tension member now. Now, if you are having this rod as an example without any holes or something in that, so this is very plain rod, we can say. Square rod and plain, there is nothing, no holes and nothing here. So in that case, this formula is applied. But if you have a problem like this, now this is a problem of the same kind, but you'll see that there are bolts here, right? There are 2 bolts, 18 mm diameter bolts, correct? Now we will solve this problem now. So there is a, let's say, plate of size, how much is this? Plate dimensions are 200 by 8 mm. So the cross-sectional dimensions, 200 width and 8 mm is the thickness of the plate. And there is a force. Now the problem is find out how much maximum tension the plate can carry. So you don't know the tension now, but you know the cross-sectional area. So if you see this, so if you don't know this portion, but you know this, how can you calculate the capacity of the member? So maximum tension capacity, how can I calculate? Maximum tensile capacity of any member. Maximum tension capacity of any member. Sigma AT permissible. Permissible stress, you know, multiply by the area of cross section provided, right? So you will get the tension capacity of that member, isn't it? Right? So if I ask you, what is the capacity of 100 mm by 100 mm rod? Please tell me. How much tension force this rod will carry? So B is 100 mm, D is 100 mm. बता सकते हैं क्या? Sigma 80 permissible, you know, 150 Newton per mm square. And what is the area? 100 mm by 100 mm. So what will be this number? Newton per mm. No, it's Newton only, not Newton per mm square. So in kilonewton, it will be 1500 kilonewton. So this is the capacity of this rod actually. This rod. If I ask you what is the capacity of 10 mm by 10 mm rod, abhi isko batao. So in the previous case, we were knowing the force. So we have calculated the actual stress. Now, if I ask you, what is the capacity of this rod? So क्या कैसे निकालेंगे? Tension
15
capacity.
kilonewton.
Sigma 80 permissible into area provided. Area provided, let's say. So sigma 80 permissible is 150 into area provided is 10 by 10. So it will be, this is Newton, so it will be 15 kilonewton, right? So are you getting this? So capacity is nothing but permissible stress into area provided. Now in this case also it will be same. It is asking how much tension it can carry. So permissible stress into area provided. Now there is a trick here. If you look at the connection, there are actually bolts. That means there, for bolts we generally provide holes in the plates, right? So that means you cannot consider this area into consideration. So the area will not be 200 by 8. So it will be minus the whole area. Yeah, area of the holes. Okay. So you can see the diameter of the hole is 18 plus 2, 20 mm is the hole diameter. So what is the net cross-sectional area? Gross area minus area of the holes. So what is the gross area? You know, 200 by 8 minus 2 into, because there are two holes, 20 into 8. So 20 is the diameter of the hole and 8 is the thickness of the hole. So to 1280. So then you can calculate the capacity, net area into permissible stress. So net area is 1280 and permissible 0.6 Fy, that is 150 Newton per mm square. So you get this 192 kilonewton. Are you getting this?
Yes, sir.
So you need to subtract this area. This area is not coming there because the plate is not having this area to resist the force. So you are having only this much portion, this much, then this one and this one. That means you are subtracting the whole area of the holes, right? Now let's go into the next example, which is something related with the angles. So let's say you are having one problem. You know that in trusses there are diagonals and so on. Let's go again there. Last time we have solved that problem. Let's say we have one truss. Supported on columns, let's say, and then this is, we can say truss kind of. So we know that this truss will have a, let me say, does it correspond to this? Yes. So this member, last time we have seen that it will carry the tension, right? I think, oh, you remember this. So this is your tension member. Because it is carrying tension, from the analysis, we can understand that. Now, if you want to design this member, diagonal member, if you look at the connection, then this diagonal member we are taking as an angle. So I will choose this diagonal member as an angle section, angle. So angle section is something like this. So let's say I am preparing the truss from you, or rather using the angle sections. It is connected to this vertical member and this. So let's say this is connected like this. This is your top member and this is your vertical member. And this is your diagonal member, which is carrying the tension. Now let's say this is a member. We have connected this member to a gusset plate and we have welded it, right? Now the problem is calculate the tensile strength of the member if it is welded to gusset plate. So we are interested in to understand the capacity of this angle member, tension capacity of the angle member. Now we are taking the sections, angle section 100 by 75 by 10 mm thick. Now how can you calculate? So what is the fundamental understanding what you understand? Yes. कैपेसिटी कैसे निकालते हैं हम? टेंसाइल कैपेसिटी कैसे निकालते हैं? अभी whatever we learned till now, how we calculate the tensile capacity?
(150 into cross-sectional area).
Yeah, so net area into permissible stress. So 150 into net area. So actually, if the angle section is used, the net area is different actually as per the IS code. Let's say, so net effective area for angles or T's in tension is something like this. So area is not directly that you take the area from the table. It's not like that. It is something little different like this. A1 plus A2K, in which K is equal to 3A1 upon 3A1 plus A2. So this is the formula, just follow this. Because that means that we don't get if 100% if area of the angle actually in calculations. So the effective area is little different. So this is the formula A1 plus A2K, that is the net effective area. Now if you go here, now what angle we are using? 100 by 75 by 10. Okay, and all other dimensions are given. So A1 is what? So if you see this, A1 is nothing but effective cross-sectional area of the connected leg. And A2 is the gross cross-sectional area of the unconnected leg. Connected and unconnected. So who is connected here? Connected to the base plate, this one. So this is connected to the gusset plate, and this is, we can say, outstanding leg, which is not connected directly. Means fully not connected, we can say. So what is the area of this leg? क्या आएगा इसका? So here you can see A1 is nothing but 100 minus 10 by 2 into 10, means 10 is the thickness of the. So see, as this angle is composed of this leg and this leg, so we generally take at the center actually. So whenever we take the connected leg area, we subtract this half portion. What is this half portion? Means 10 by 2. We are only interested in this hatch area. This is connected area leg. And here also, I will consider this. Only this width into thickness. And in this case, this thickness into this width till this. So half I am subtracting. So you will see here 100 minus 10 by 2. 10 means thickness by 2 into 10 is the thickness of the member. So I think ये हमारा 10 है. Then this is your 100 minus 10 by 2. Why 10 by 2? Because I am taking only at the center. यहाँ ले रहा हूँ मैं, this one. Correct? Then this is 950 mm square, and outstanding leg is 75 minus 10 by 2, because ये हमारा 75 minus 10 by 2 means यहाँ तक ही ले रहा हूँ मैं, this one. Okay. So this is your 75 minus 10 by 2. Are you getting this? How to calculate the connected leg and area of this?
Yes, sir.
Okay. Now, once you get the A1, A2, then you just put it into the formula. K is equal to 3A1 upon 3A1 plus A2, which comes out to be 0.8. And if net effective area is A1 plus KA2. So A1 is the connected leg area, A2 is unconnected leg area, and this is the factor K. So you get this effective area. Then A net into permissible stress is nothing but your capacity. Got this? समझ में आया?
Yes, sir.
Next one is the Now the problem is little different here. So instead of welding, we are putting the bolts here for this connection. Now, what will happen in this case? Tell me. क्या होगा इसमें? There is a hole. That means you should subtract the whole area, right? So area of the hole is how much? ये इतना minus करना पड़ेगा ना? This. What is the diameter of this bolt? 20 mm. So we can to calculate the whole diameter, we can add 2 mm into that, because we know that the hole is little larger than the bolt size, correct? So let's say 20 is the diameter of bolt plus 2 is the diameter of the hole. So area of the connected leg will be 100 minus 22, because this is not available now. The cross-sectional area is only this much. This much only. This much. Then till the half portion here, this much. And you need to subtract this part also, correct? So that will be 22. We will subtract this portion only. So you can understand here. 100 minus 22 minus 10 by 2. 10 by 2 is the thickness. Okay. Into 10. Other things are same actually. Unconnected leg is same because there is no hole in that. And then you will calculate the K, and then you will calculate the tensile capacity. So are you getting this? Got this? Now again, same thing. If I ask you to calculate the capacity of tension capacity of this rod. So the diameter of this bar is 20 mm. Now this bracing is developed by 20 mm diameter rod. So how to calculate the capacity? Net area into permissible stress. Net area is very easy. Pi by 4 d square. That is the cross-sectional area of the bar. Generally, if you have the horizontal load like this, then you will have that this will go in tension. So this will be your tension and this will be your compression. So we are only concerned with the tension member design for this time actually. So we will go for the compression design also after that. So have you got? Okay, समझ में आया कि tension member design कैसे रहते हैं? It's very simplest design in the steel structures. Yes. समझ में आया?
Yes, sir.
Yes, sir.
Now let's go to the next problem, that is compression member design. So tell me. So definitely compression member design is different than the tension member design. And why? Tell me. अभी ऐसे समझो ये there is a column supported on some support, let's say like this, and there is a force like this P. So tell me what will happen to this column if you apply the force like this? क्या होगा इसका? If this is your original length L, ये क्या होगा इसका?
Delta L reduce.
So the length will be reduced by delta L, let's say some changes will be there. So your original length is L and the final length is L minus delta L. That means it is a shortening effect. The column will shorten. As it is shortening, then there will be compression. So all of you know this now. Term. Philosophy is very easy. Now the material is steel here. Now can anybody tell me what is the what is the capacity of the column? बताओ logically. So any capacity of the axial member, how we calculate? Effective area into permissible stress. Yes, यही है ना? टेंशन में ऐसे किया था ना, नेट इफेक्टिव एरिया इनटू कॉम्प्रेसिव स्ट्रेस, परमिसिबल मींस परमिसिबल स्ट्रेस रादर. तो फिर व्हाट वैल्यू वी कैन टेक दिस इन दिस केस, क्या लेना चाहिए अभी? मटेरियल तो स्टील ही है ना. Can I take 150 Newton per mm square in this case? Because the material is same. Yes or no? We cannot take this capacity permissible stress actually, because what happens in compression members, due to the loads, there is a possibility of buckling of the members. So what happens after, if you apply the force like this, at certain point it may happen that it will buckle. That means before reaching to its full capacity, this is your full capacity of the member actually. Before reaching this, it will buckle. That means I cannot take the full capacity. So that means there is a reduction in the capacity. So reduction in the permissible stress, either capacity or stress, reduction in permissible stress. And why there is a reduction in permissible stress? Due to buckling. समझ में आ रहा है? So why it buckles?
Slenderness ratio.
So it is buckling due to slender member actually. So this is a natural phenomena. We are not inventing anything actually. So we know that if you apply force to any member, compressive force to any member, it will try to buckle. But technically why it is buckling? So it is something related with the slenderness ratio. Slenderness ratio we generally denote by lambda, which is nothing but L effective upon R minimum. So what is R minimum? पता है कि R minimum क्या रहता है? It is something property of the cross section. What is that?
Minimum size of section.
So it is square root of I upon A. This is a formula actually. We learned in the mechanics actually. R minimums, we call this R is nothing but radius of gyration.
Yes, sir.
Radius of gyration. And the formula is I upon I. I is the moment of inertia and A is the cross-sectional area. And what is L effective?
Effective length of member.
Effective length of member. Of length of member. So it is something, we can say it is something related distance between the point of
Point of
contraflexion, we can say.
contraflexion.
Right. So let's see क्या होता है ये. समझो, we are having one column like this. For the time being, I am taking this, and it is fixed from both the ends, and I am applying a compressive force on this member. So there is a fixity on both the ends. So it will try to buckle like this. So क्या करेगा? As due to the fixity, it will not buckle here, but it will buckle after some portion. Till that point, it will be something like this, and then it will buckle. Okay. Again, it will buckle here. So if I show it in line diagram, it should look like this. ऐसे कुछ तो होगा, and then it will buckle, and then again it will. You know that the buckling or bending is starting from this point, and again it is starting from till this point. So the bending is between these 2 points only. Within this range, it is not buckling. So that means whatever is this length, we call it as a L effective. And this is your total length of the member. This is 2D diagram, this is single line diagram. So L effective is something related with some coefficient. It is reduction in the length, we can understand. This is less than capital L, right? So it will have some coefficient into original length. Correct? We can say L effective is some reduced. It may not be reduced always, but coefficient into L. Getting this? Where we get this R value? R value we can get it from the steel table because it is a cross-sectional property of the section. Steel table, if you refer IS code, IS 808, then you will see this I values and R values also. Everything will be there. I values, A values, and R values all. Okay. Now R minimum it is saying. So now let's see. L effective समझ में आया क्या? Now there is one. That means we can say that L effective depends on boundary conditions. Depends on boundary condition. Boundary means supporting conditions. Instead of fixed support, let's say I am having a hinge support like this. Hinge. Both are hinged, let's say. That means this is a pin, this is a pin. And if you apply load like this, then it will try to buckle from here itself, right? Because this is we can say it can rotate at this point. That means the rotation will start from this point itself. In this case, I can say that L effective is your L. Correct? Getting this? So as per the boundary condition, this L effective goes on changing. Now you will see all these L effective values in the IS code. They are given in IS 456 also and IS 800 also. Let's see that. So in this table 5.2, 800, you will see the effective length values given already here. So effectively held in position, restrained against rotation at both the ends. I mean, this is a fixed. If both the ends are fixed, then this value is 0.65 FY, 0.65 L. If it is a hinge at one end, fixed at the other end, 0.8 L. If both are hinge, 1 into L. So we have seen that already. If it is a cantilever, then it is a 2 times L. If this is a free end, we can say. And if it is a hinge, then it is 2L. If it is a fixed, so there are different conditions given here. We get it from the IS code. Now R values. So we are interested in this L effective and then R values. So R values, what is R or what is moment of inertia? Let's see in detail first. So let's say we will take an example of I section in this. I section है ऐसे कुछ तो. So this I section is having some area cross section तो है इसको. Then we generally find out the properties along two axes of the member. So let's say this is your x axis, this is your y axis. So there will be two values of moment of inertia, Ixx, Iyy, right? Then there will be, so you know that Ixx we can calculate from the basic principles. And then there will be two values of Zxx and Zyy. Z मतलब क्या है बताओ? ये क्या है? Moment of inertia about, so this is moment of inertia about x axis, this is moment of inertia about y axis, and this is section means what? Zx means
Section modulus.
So what is the formula for this? Ixx upon y. This is Iyy upon y. Y means this distance, right?
Yes, son.
Now there is a one more thing. There will be Rxx and there will be Ryy because there are two axes. So Rxx will be Ixx upon
A.
and Ryy is Iyy upon.
Iyy by A.
Yeah. Now tell me, if you consider this I section, which moment of inertia is more? Ixx more hai ya Iyy more hai? Who is more? If this depth is more and this is your width, generally in I section, the width is less and depth is more. So if the depth is more, then Ixx more रहेगा या कम रहेगा? Yes. ज़्यादा depth है इसलिए ये this is more and this is less. Less means compared with this. Correct? That means Zxx will be more and Zyy will be less. Now tell me Rxx more रहेगा या Ryy more रहेगा? Who will be more in this?
Rxx.
Will be more. So this will be more and this will be less. That means R minimum क्या रहेगा इसमें? Who is R minimum?
Ryy.
Ryy. Okay. So this is very clear from this. Looking at the section, you can understand that Ryy will be less. And where we get these values, we get it in the steel table. So it is given in the IS 808. So there are for different types of sections, angle, channels, I sections. So this is the I section here, XX, YY. This is a depth, this is a width. Here you can see. Let's say MB 100. MB means ISMB. And you see the depth D is given here, width of the section is given B. T is the thickness of the flange. Capital T is thickness of flange. Small t is the thickness of web. So we call this as a web and this as a flange. Okay. Then we get this. These are the radius R1, R2, this radius. So we are not bothered much about this. Now there is a IXX, IYY. It is given 183 is the IXX and 12.9 is the IYY. You can, looking at these numbers, you will understand IXX is more than the IYY. Then again, RXX is 4, RYY is 1.05. So RYY is minimum. And Z also you'll see 36 is the Z, XX and ZY is 5. That means ZX is more. So it's very, we can say, common sense to understand this. So in calculation, you will require RYY here because RYY is the minimum value, 1.05. Correct? So till this, it is clear to all of you. And where we get the cross-sectional area A is here, 11.4. See, all these values are given in centimeter. So cross-sectional area is given in cm square. Moment of inertia is given in cm raised to 4 and section modulus in cm cube and R value in cm. Please try to understand the units. Don't forget these units are different. Okay, generally we are comfortable with the mm values, but steel code is giving this cm values. कोई बता सकता है cm में क्यों दिया, mm में क्यों नहीं दिया ये? Common sense बताओ. Why it is given in centimeter raised to 4? Why not mm raised to 4?
So वैल्यू बड़ी हो जाती फिर
हाँ
डिस्प्ले
बड़ी हो जाएगी. 10 रेस्ट टू, अभी ये cm रेस्ट टू 4 मतलब इसको 10 रेस्ट टू 4 से मल्टीप्लाई करना पड़ेगा. That means 40 angle. So if you put 4 zeros to this, then the table will be very big. So to fit that table within that page, they have taken this shortcut. Okay. It doesn't make any difference. In calculation, we will multiply this value with the 10 raised to 4. Okay, so we will see that. So in compression member, now you might have understood that. Okay, so till this, everything is clear. All properties are clear to all of you. Now tell me, if this is a column, so there are two columns. One column is having length as, let's say, 3 meters, and second column is having length as 6 meters. Now tell me, who will have more capacity? Yeah, first wala or second wala? Who will have more capacity?
First wala, sir.
First wala, yes. Because the second one is having more length, that means it will try to buckle more. So this is very clear to understand. If the length is more, it will buckle early. As it is buckling early, then its capacity is less. It's very easy. Now I am going to ask you certain questions. Lambda is L effective upon R minimum. So if the slenderness ratio is more, capacity will be less or more. So let's say this is your lambda and this is your capacity. So if the slenderness is more, capacity will be more or less?
Less.
Less.
Will be less. Simple. Okay. That means now there is one question. If length of the member is more, then capacity is
Less.
then if the R minimum is more, the capacity is
More.
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 because it is in the denominator. Please try to understand. That means if you want to increase the capacity of any compression member, either you should have less length or more R minimum. Are you getting this? एक तो लेंथ को बढ़ा लेस करो, कम करो, या आर मिनिमम को बढ़ाओ. Yes or no?
Yes, sir.
So try to
Yes,
reduce
sir.
the length or try to increase the R minimum value. Now you can, if you go into the steel table, how can you increase the R values? How to increase the R values? We cannot increase the R values. We can change the this section and then you can see. For example, is MB100 is having RY value is 1.05. MB125 is having 1.5, 1.57, 1.7. That means as you go on increasing the size of the member, R value is getting increased. That means there is only choice to increase the R is to change the section to the higher side. Okay, now there is second question that if you want to reduce the length of the member, what can you do? Okay, you know that if you reduce this value also, you can increase the capacity. ये कैसे कम करेंगे length?
Bracing.
Not bracing exactly, but I would say tie.
Support.
Tie. We can say, so let's say there is a frame like this, for example. समझे एक column है, frame है समझो. Let's say this is your frame, which comprises of two columns and beam having length L. This length is L, let's say. Now, how can I reduce this length? I can just add one more beam over here. Then what is now L? This L is nothing but L by 2. So half कर दिया मैंने, right? That means I have reduced the length of the column by adding this tie member. So you can add this tie beams in between the columns and you can control the length of the member. That means you can tie anything. It may be you say tie beam or whatever you want to say, but add just member so that previously how it was buckling. समझो ऐसे मैं निकालता हूँ यहाँ. So one case is this. In this case, the column will try to buckle like this. Let's say, if you consider this as a fix, then it will buckle like this. And this will be your effective length, correct? For this case. And what will be the effective length in this case? इसमें ऐसे then ऐसे कुछ तो आएगा ऐसे. So now this is your effective length. Try to understand this. Huh? Getting? So effective length got reduced because you have reduced the L itself. So this is
Yes,
this
sir.
kind of techniques you can use to increase the capacity of compression members in any practical structures. Try to understand the concepts, how we do in practice, then you can think over that. Now I think everything is clear. Now we have also learned that means the capacity is depending on the lambda value, which is L by R. So if the lambda is more, capacity is less. That means sigma AC permissible will be less या more. कम रहेगा ना, capacity less मतलब this is less. So the code has given these values sigma AC permissible as per lambda. So you need to calculate this lambda value in the design, and then you get the sigma AC permissible from the code. So it will be different for different lambda values. That's it. Okay. Now let's go to the example. So this is clear to all of you. We will share this PPT to all of you. So we get this permissible value from this formula, but we are getting directly from the table itself. अभी कैसे करेंगे बताओ? Let me take one simple example first. Let's say we are having one truss and there is a member which is carrying the compression. So in design, we know that we have to assume certain cross section, and then we will check that cross section whether it is safe or not. So how much compression an inclined member can carry? And the member size is 50 by 50 by 6. And the length of this member is 3 meters and connected by welding. Okay. So what we need to calculate? So we know the cross section, that we get the R minimum value from the table, steel table. So this 800 you will get those values of the R minimum, 808 angle के लिए जो है वो. Okay. So here you will get these values. So there are I values, R values, R minimum. See, in this case, there is a peculiarity here. In angle section, the R values are not only RXX and RYY. There is RU and RV. So generally we get R minimum value as RV. See, I think ये पता रहेगा. As it is unsymmetrical section, there are 4 axes, one XX, YY and UU and VV. So generally we get the minimum value as RV. So see here, they are writing here minimum. So we will take this value RV as a minimum value from this table as per the cross section we are using 50 by 50 by I think 6 something. So that value comes out to be 9.6 mm from the steel table. Area of cross section also 568 from the steel table. L effective is 0.85 L. Generally we take it little higher actually values. We know that because this is not exactly hinge and this is also not exactly pinned. I know that we generally consider the trusses to be simple, we can say only axial force member. That means two ends should be hinged, but we take there is a partial fixity available most of the time, so we can take 0.85 L here in this. Then lambda is L effective upon R minimum. L effective is 0.85 into L. L is 3. 2.55, 250, divided by R minimum, 265 less than 350. Okay. For this is your slenderness ratio, which is coming out to be 265 here in this case. So sigma AC we get it from the table. Let me show you. 5.1, I think 5.1 is given here. Permissible stresses in compression. Okay. Now what is your it is given here Fy is equal to 250. So our grade of steel is 250. So we will take this value and lambda is here in this direction. Now actually yahan, in this case it should not be, it's not right actually. Now I will tell you, actually generally we don't allow this slenderness ratio more than 180. Yeah? So keep in mind, generally we don't allow more than 180 in this 265. Abhi for time being, let's take that example. इसमें नहीं दिया होगा मेरे ख्याल से. So here you can see 250. So it is more than 250. So we have taken this as a 18, right? दिख रहा है यहाँ? Our value is 265. Ideally, we don't allow the slenderness to be more than 180 actually. So यहाँ तक ही करना है, यहाँ नहीं करना actually. But अभी let's understand the process first. So our lambda value is 265. So we will take 18 value, right? Here. If your lambda value is let's say 120, then you will take 64 as the permissible stress sigma AC. Getting? समझ में? Once you get the permissible stress, multiply that with the area of the cross section, you get the capacity. So does the procedure clear to all of you?
Yes, sir.
Now I will ask you, as I know that I want this value to be less than 180. क्या करना पड़ेगा बताओ? L upon R I want less than 180.
Increase R minimum.
Area बढ़ाना.
Because see, we cannot change the length because this is a geometrical, we can say, property of the truss. So we can't control this. Yes, there are ways I can have one pi member, but generally it is not done in trusses. Generally, I'm saying it's not hard and fast. But yes, I can change the R value by increasing the size. So instead of 50-50, I can go for 75 by 75 or 100 by 100. And then this value will reduce. Correct. So this will reduce. R will be more, then this will be less. Let's say I get L upon R value as 150. 150 आया समझो lambda हमारा. What is the permissible stress for 150? यहाँ 150 है हमारा lambda. It will be 45. So 45 into area of cross section will be the capacity. Got this? Simple permissible stress into area. That is the capacity. But permissible stress is different, which depends on L upon R, lambda. Similarly, there are certain problems having some different cases actually. If they are connected by the gusset plates, now it is asking design a double angle discontinuous strut to carry the load of 90 kilonewton. The length of the strut is. So the two angles are placed back to back with long leg. Can you see this? See, in trusses generally we are having compression top chord member and tension bottom chord member like this. Double angle we generally use, and diagonals we use single angles generally. So if this is the case and this long leg is, let's say this connected leg is long, our problem here you can say the two angles are placed back to back with long leg connected and are bolted. ये समझो long है ऐसे, and they are connected and bolted. So if this is the case and if it is carrying compression, so there are certain different clauses given here. L effective, R minimum, you know how to calculate all these things. Then sigma AC how we calculate, say let's say L upon R इसका कितना है 119 है. 119 is the slenderness ratio. So how to calculate permissible stress? 119. Now actually we are having only 120 and 110. So we can interpolate in between these two, between 110 and 120, and we can arrive at the, so 110, 120, and this is 119. So interpolation formula, then you get the sigma AC, and then you can multiply that with the area into permissible stress. This is your area, this is permissible stress. I hope you got this concept. Any questions?
No, sir.
Okay, so today we will close early actually. So I hope you practice this manually at home. You take any arbitrary example, or you can try this example also.
सर ये पीपीटी सेंड ग्रुप में कर दीजिएगा.
हाँ कर, we will share on the classroom. Okay.
Okay, sir.
Just give the message on the group. So we will send it from the office. Okay.
Okay, sir.
Now actually compression member, tension member, can you give me examples where the compression comes in any structures, general structures? कुछ भी example बताओ जिसमें compression है, tension है. So the example of tension member, examples of compression member बताओ कहाँ कहाँ आता है?
So struts में आता है सर compression member. Interest.
Yeah, so yeah, first very simple example is nothing but a column. Column में आता है पहले, simplest example. Any column can carry. ठीक है, ऐसे ही निकलता हूँ मैं. Single line निकलता हूँ. So this is a column, and then it also carries compression. This is a compression member. Then let's say there is a frame, and this is a column, so it is a compression member. This is compression member. This is a beam, so it is a bending member. Then compression का example, truss. Truss maybe we have seen that if you develop the truss and this kind of direction is there, then you get compression here. Where else you get the compression? और कहाँ आएगा आपका compression? Yeah, ये member top chord. So this will have a compression top chord. This bottom will have tension. Right?
Yes, sir.
If you have this diagonal member in some different direction like this, then this will be tension member. This one. Right? So in trusses we get tension, compression, and also
vertical members.
Yeah, vertical members. Vertical members, many times we have compression, but yes, sometimes we get tension also. So this is the truss. Then we have seen that you might have seen the suspension cables in the bridges. There is a pylon, and the bridge is suspended by the cables. So the cables carry the tension. So this is one case. Then we know that in canopies, entrance canopies देखे होंगे कभी भी. So there is a, let's say building is there, and there is a cantilever coming like this. Let's say there is a first floor, ground floor, and this is the entrance. So generally the canopies are suspended by the rods or cables. It may be rod or cable. Cable or rod. So this is a tension member. So these are the general examples of tension and compression members. और कोई है क्या example?
Bracings.
Bracings, yes, correct. Bracings. So if there is a horizontal load, generally we do it for. So if this is a horizontal load, then we have a tension here and we have a compression here, right? So this diagonal will carry tension, this diagonal will carry compression. So bracings, yes. Or if there is an arch like this, what force it will carry? It's a load is some vertical. What is the dominant force in this?
Compressive.
So it will be compressive. So the arch carries mainly compression. Definitely there is a bending, but it is little bending. So the arch is a compression member, we can say, mainly. So in any structures, whatever you consider, this is the philosophy. Philosophy doesn't change. If you want to calculate the capacity of the cable, net area of the cable into permissible stress, sigma AT, as per the code. If you want to calculate the compressive capacity of this rod or bracing, then calculate the L by R, calculate the L means lambda L effective and R minimum, and then get the sigma AC from the code. That's it. Here also, arches also, L upon R and then sigma AC from the code. Even this also. Only in this suspension bridges, actually the Fy values are actually higher, very high. In this, they are high tension cables actually. So Fy value may be more than 1000, like 1200 Newton per meter. Okay. Only the Fy value you need to check what material you are using. It depends on that. That's it. Trusses is also same and column is also same. So you should know the Fy values, what material you are using, and then just follow the code. Now let me ask you some tricky questions. Let's say design is very easy, so I'm not going much detail. I hope you have understood this. There is a I columns here. There is a structure like this, which is connected by the beams. Okay. And let's say this is C1, C2, C3, C4. If you see the elevation, it should look like this. Now I'm drawing the elevation like this. I say cross section or elevation. So if you see this, then it will look like this. So double lines again, I say there will be double lines. Then connection by the beams, and again double lines. Double lines, why? Because ये flange है ना उसकी. There is a flange. ये मेरा C4 है और ये C3 है समझो. Not C3, C2 ना. C4 and C2. Okay. And this is your I section. Now let's say this height is 5 meters for the column. Now if I ask you, if I want to increase the capacity of this section, I section मैंने समझो same constant size लिया, let's say ISMB 300 for example, this column section. I want to keep this section as it is. How can I increase the capacity of the member?
Using bracing.
Tie beams.
Tie beam.
So कहाँ देंगे tie beams?
Diagonal sir or center?
Center of column.
यहाँ ऐसे देंगे? Yes. So ये 2.5 हो जाएगा, right? So is it correct? Do you think so? It is correct. If you see the plan, it looks like this. ये मेरा plan है beam column का. This is also column plan. And then it is connected by the beams. So I'm putting tie beam in this direction. So is it correct or not? See, you should, your column is governed by the minimum value of the R value. So which is the R minimum value? Is it RXX or RYY? ये मेरा XX है, correct column का. And this is my RYY. Yes or no? So should I tie RXX value or should I tie RYY value? So in which direction I should tie? So this is not the right way in the beginning, because your column design is governed by minimum value of the R, which is nothing but RYY in general. So this I should tie like this, not like this. So this is very critical point actually to understand fundamentally. ये मेरा है ना structure ऐसे. I am having this structure like this. So I should not tie like this. Additional tie what I am saying in this direction. So instead of that, I should tie in this direction, which will tie the minor axis of the column. So this is very important to understand from the concept point of view. I should tie like this, so that what will happen? My RYY value will reduce. Yes or no? Because not RYY value, I mean to say L upon R minimum we are concerned. So L will reduce. 2.5 हो जाएगा और R minimum तो same ही है for cross section. So are you getting this? Because generally we have a RXX. So that means we can say if you design this column, you should design the column by two conditions together. One condition will be L effective upon, let's say you are putting tie in this case. So L effective upon R minimum. So let's say we don't have this tie. So in this case, what you will check this L effective upon Rx here in this case. And in this case, you will check L effective upon RYY, and L effective here you will take the 5 meters. Here you will take 2.5 meters. So that means it is governed by this actually. So this is your main governing tie member, not this. समझ में आ रहा है कुछ? Are you getting all of you? So we should give the tie to the minor axis first, because it is governed by the minor axis. Imagine that if you are having a compressive force on this column, so let's take an arbitrary example again. Let's say this is a column in plan and you are having compressive force, which is normal to this plane of the paper. So definitely in the direction of minor axis, it will try to buckle. So this will be your buckling direction. Minor axis पे ही जाएगा ना buckling. Let's say I will give one example so that you may be understanding it. So let's say this is your scale, which whatever you use for drawing the lines. हमारे plastic scale रहती है ना. And if you apply compressive force like this, just you push this scale by using your palms, then definitely it will buckle in this direction. So if I draw the cross section, so ये मेरा cross section है. So there are two elevations. One is this elevation and second is this elevation, right? And there is a compressive force. So definitely it will try to buckle in this direction, not in this direction. Yes or no? It will not buckle about the major axis. It will buckle like this. Are you getting this? What I'm telling? समझ रहे
Yes,
सभी को?
sir.
It will
Yes, sir.
buckle about the minor axis, not in this axis. So that means what you will do, you will tie this in this direction, not in this direction. Yes or no? यहाँ tie नहीं करेंगे ना आप, इसको करेंगे, because it is buckling in this direction. So the direction in which the column may buckle, you need to tie first. I hope you are getting now. जिस डायरेक्शन में बकल हो रहा है वहां टाई दे दो. So you practice all of you on the basic concepts of this. and imagine certain structures, real structures, कि वहाँ क्या होता है, मतलब what is happening there. And you observe the structures surrounding you, RCC building, steel structures. You can go on the internet, you can Google different structures, steel structures. Then you will see what is happening. You just try to imagine where is the compression, where is the tension, and why the members are developed that way. You can ask me question in the next section also. Okay. Any questions? कोई डाउट्स है क्या? Hello.
No, sir.
Okay, so shall
Sir,
we?
sir, 1 minute.
Uh-huh. Yeah,
Sir, when we calculate the tension capacity, we use for angles this net area.
right,
So,
right.
yeah, in compression also net area we are using, or is there any difference?
No need of net area, but for angles actually, yes. Generally what happens whenever there is a compression, the holes gets try to compress actually during the bolt zone, right? So generally there is no need of any reduction. Okay. So they
Okay,
will
sir.
try to come closer to each other actually. In tension, they will try to go apart.
Okay, sir.
Okay.
Thank you, sir. Good night, sir.
Thank you, and see you. Prepare that truss model, whatever I told you last time, and try to design that member by this method. Okay. So you can
Yes, sir.
model on the Staad Pro and get the tension forces and compression forces from the Staad Pro and design the member for that. Okay. You can assume angle section for the time being and design it. Okay. Fine.
Okay,
So
sir.
thank you all.
Thank you, sir.
Thank you, sir.
Good night, sir.
Thank you and good night to all.